All right, we're going to go ahead and return to our speakers. So next on our list is Dr. Bluntzer, the Executive Director of the Hamm Institute for American Energy. Please help me in welcoming Dr. Bluntzer to the Great Plains Center Excellence Conference.
Thank you, Jessica. Hi, it's great to have you all here in the building. It's always a good thing when you've got a lot of like-minded people in one space trying to hear a little bit about what each other's doing in your different fields in this industry. And of course, I would argue, and none more important than the energy sector. That's what we try to do here at the Hamm Institute, is really be a place where ideas can convene and thoughtful conversations about coming up with solutions to help secure our energy future can happen here under this roof, physically, obviously, but then more importantly, once you leave here today and the conversations can continue. Our hope is to always be an organization that you can reach out to if you need assistance with whatever projects you might be looking to pursue. Today's focus is obviously on workforce development, which I'll go a little bit more into that. That's actually my background is in organizations and how they function. But a little bit about the Hamm Institute, this building and the history, if you're not familiar with it. It originally, Mr. Harold Hamm in Continental Resources gave a very generous gift to the university, to Oklahoma State University, to found the Hamm Institute for American Energy. The building actually was donated to OSU separately and a gift prior, and the two together are now where you're at, the Hamm Institute coming together in partnership with Oklahoma State University. You'll see several booths around today. I've been here for exactly 30 days. I'm brand new in this role, and so I'm even learning about which departments are represented here for Oklahoma State University today. But know that in my short time here, I have been unbelievably impressed with the skill level of our faculty and our students at this university. I just was sitting with three of them, got just a few moments to visit with them. Ryan, Ryland, and Hayden, all engineering students at OSU. And one of them was sharing with me, Ryland was, that he actually has started his own 3D printing business in his garage with 7 different 3D printers. Has all these orders, and it's asking him what he's going to do next. What is he excited about? What kind of jobs are these 3 gentlemen going to be pursuing? And they aren't sure yet. And I think that is unbelievably indicative of why you came here today, to maybe understand and learn what are the challenges of finding a workforce to help meet the needs for the clean energy future. And when I say clean energy, don't be mistaken, I mean all of it. I think every single source of energy, below the ground, above the ground, whatever it is, has the opportunity to be as clean as it possibly can. And it is our responsibility as human beings on this earth, and for me, working for a university, teaching the next generation, these 3 gentlemen specifically, to make sure that we are doing the most that we can to ensure that. I love the Sustainability Alliance over here, People, Profit, Planet. I thought that's very telling. I actually use those 3 words a lot in some speeches I give around what the responsibility is for us as consumers of energy, but more importantly that we are then providing it to the consumer. And that keeping those 3 things in mind are ever present. At the Hamm Institute, we're going to continue to push forward from an economic lens. Does this make sense? Can people make a profit off of this? How does the renewable energy space and clean energy solutions, as they're typically known or traditionally been defined, interact and add value to some of the more traditional energy sources? When our world is currently being powered by almost 90% from traditional energy sources, there's a responsibility for everyone in this room, especially these 3 gentlemen, to figure out a way to make it cleaner and greener so that it continues to be something that we can provide the rest of the world to have sustainable, economical power, right? That's what every human being on this earth deserves. And so I will always advocate for for, the Hamm Institute will always advocate for, and OSU, speaking broadly here, will always advocate for teaching young minds in your future workforce how to make sure we're all working together and not against each other in the way things are getting funded, capitalized. I got to hear the panel this morning. I thought it was fantastic. Gentleman from the DOE. We had, I think it was I put a big star by her name, Dr. Sharon Harrison. I loved her point when she was talking about the current workforce and what they value and what's important to them and how you're going to be able to attract them to a job that's probably very different than maybe what attracted you to the first job that you ever had. And sitting here thinking, okay, we got an entrepreneur here, he's an engineer. There aren't that many engineers that think they can go down an entrepreneurial path. That's a pretty unique skill set. You know, are we building business and opportunities within our organizations to attract someone like Ryland? Think of your company right now and who you're here representing. Is there a spot for someone like Ryland that can come in with that entrepreneurial spirit and be successful? Or will he come in and be another peg in the wheel? Like how can we rethink how our businesses are structured to make sure it is attractive to these young people and what's exciting to them? How do we get them excited again about traditional energy? That's a big thing I'm passionate about. We've got empty petroleum engineering jobs all over. The majors have gone down, specifically in our public land-grant universities. Our petroleum engineering numbers continue to decline, but yet we are still producing and exploring at a rate that is at least stagnant, and last year was actually up 1%, when everybody, including the IEA, said it was going to go down. It has not. It has stayed consistent and gone up slightly. It's projected next year to go down 2%. Point being, we're not properly educating our workforce to get them excited about all the different options they can have in an energy future. And every single major energy company, the 5 big multinational energy companies, are invested in all of it. They're invested on the traditional fossil fuel side, they're invested on the renewable side, they're invested on the nuclear side. I just returned straight off a flight from Seoul, Korea, working with my partners here. Andrew's here, but John is from OSU Global. And specifically, our whole mission in being there was how do we help Asia, Japan, and Korea, both highly developed economies, how do we help get them to a place where their energy future is secure? Because it is so vulnerable right now in that part of the world, in China's influence, and what could happen to their economies if they go all in on getting what they need for one country. Trying to help them diversify that, understand those vulnerabilities. All of those things, I think, are things that could get exciting to young people if they understood the full circle of what it means to have secure energy. If they knew that they could be a part of the policy decision and that their vote actually impacts what that looks like. If they knew there might be a role at a big company for them where they could explore their entrepreneurial spirit. If they knew there was an advocacy role for them in some place in one of these organizations and they're that passionate about it that they can go and talk about it. I don't know that our young people know that they have these options out there and that there are companies that can give them that space. And if you're working with a company and have any kind of direct influence on what new first-time roles into your organization look like, I want to challenge you to rethink them. Just go back to your basic job description, anything you have listed within your organization right now. And I want to challenge you to go home and talk to whoever you need to talk to at least change one descriptor, just one descriptor in the job description that you think would align with someone in this younger generation that would get them excited about coming to work for you and your company. And don't go down the traditional route. You need to have knowledge of this software. You need to have experience in this. Think outside of the box. What's exciting to them? How do I get someone like Ryland to come work for me in my organization? And are the jobs that we are putting out there even looking like they're reflecting that? So I focused a little bit more on the human capital piece because I know that's the side that you are here talking about today, and really trying to figure out how we're gonna be able to get people in this industry and get them excited about providing the energy that is needed. I ask all of you to lean in wherever you're at to your universities. or whoever you have an affiliation with. OSU is obviously very welcome, and we'd love for you to tap into our resources and our faculty and our students. We believe we have the best here, and would love for you to give us the opportunity to highlight that. You're in a building right now that is almost vacant. Even have Baker Hughes, who is currently doing their R&D work here in the lab here and the well here on site, and they are now exiting their research facility here, and that will get turned over to OSU as of October 1st. And so we have an actual research facility right here in Oklahoma City that has the capability to do, you'd be shocked at what can happen down in that lab. And so we'd love to be a resource for you for that as well. So if there are things you're excited about testing, you want young minds and grad students and our faculty around some of those ideas, please let us know. We're excited about the opportunities we're going to have to do that. Again, welcome Oklahoma City, welcome to the Hamm Institute. And if we'd love to be a part of your futures as you grow your companies, and please don't hesitate to reach out if you need anything, all right? I'll turn it over to Jessica. Okay. Sorry, I brought up this little piece. It's on the back table from the International Trade Development Organization. Fantastic book. I would recommend grabbing one. Gives you a very accurate and honest research of data kind of on the role that fossil fuels plays and where the opportunities are, specifically in the back half of the book, and how it can play in concert with the renewable energy space. So it's a great read. Please grab that, and of course all this stuff's probably online too, but forgot about that.
And thanks so much for the Hamm Institute and your commitment to being a partner for the Great Plains Center of Excellence. We're going to go ahead and invite Mr. John Cummins up to the stage for the keynote presentation. He is the Executive Vice President of Product Technology and Investing Partner of Hydrotex LLP, a Texas specialty lubricant and chemical company founded in 1936. He's responsible for research and development, technical services, and is the Dean of the Hydrotex Lubrication University. Mr. Cummins has 40+ years of experience in the chemical additive and lubrication industry. He's a retired captain in the Naval Reserves with a military career spanning Vietnam through Desert Storm. He's taught over 300 public classes on lubrication and grease science and lubrication excellence. I know we're pleased to hear from him today.
Thank you, Dr. Bluntzer, for your passion. It's intuitively obvious that she's passionate about this institute, and it's a pleasure to be in front of you guys today. I want to talk about lubrication's impact on sustainability. Dr. Flora came to one of my classes, and we started talking, and your group did an energy audit of our manufacturing plant, which we incorporated those expenses to save some money. But there are other significant savings out there other than just changing light bulbs and moving in or trying to make your building into a LEED certified building and things like that. And I'm really promoting a focus for this group to take a look at, so that's why I'm really here today. The agenda, energy consumption caused by tribological contacts. That's the nerdy way of saying we've got a lot of friction wear out there. We'll be looking at combating energy logging wear mechanisms. We're going to do a very simplistic approach since it's only about 20 minutes. And then I'm going to talk about a $233 billion target of opportunity energy savings. Maybe one of the reasons why we're here. Then I'm going to talk about some interesting technologies that are coming around. We'll be talking about 3D mapping of facilities for energy audits, lubrication and maintenance of programs, and maybe about some biosynthetic fluids replacing petroleum products with synthetic bio-based fuels. So last year we produced 1.4 quadrillion BTUs of energy in the United States. Okay, almost 20% of the world's energy. And I travel, and when I've traveled internationally, people always say, well, you're an American and you guys use up so much electricity and so much energy. But I also say, yes, I'm American, and we probably develop 50% of the patents worldwide. Okay, and if we're going to develop 50% of the patents worldwide, we need to be using our energy more responsibly and show other people how to do the same thing. So we get about 36% from petroleum, 32% from natural gas. That's not going to go away for a long time. About 13% renewables, 11% coal, and probably a really black mark on this country is we're only producing about 8% with nuclear. And then, 3 Mile Island movie to probably blame for that. So if anyone know what a British thermal unit is, it's the amount of energy to increase 1 pound of water, 3 Fahrenheit. If we took all of the energy that we produced last year and heated the Great Lakes, we could raise it 1.5 degrees Fahrenheit. So that's a lot of energy. A lot of energy. So transportation, about 1% from nuclear, that would be the nuclear aircraft carriers and submarines we have in our naval forces. About 5% from renewables, 4% from natural gas, and 90% from petroleum. That's a big number that we have this green. That if we want to replace that by 2030, it's going to be a big pull. Sources used by industry, which is what we're going to be focusing on. We're getting about 4% from coal and nuke, about 9% from renewables, 40% from gas, 34% from petroleum, and 13% from electricity. And that really surprised me. That industry only uses about 13% of electricity, but when you realize of all the thermal energy that's required to make steel, okay, to use heat transfer systems for liquid blending and things like that, then it really starts to make sense. So these are big numbers, but we really need to understand to get our hands around the problem. If you don't know how big the problem is, it's kind of hard to solve it. Now we take a look at electricity, which we all want to save. And we produced 36.7 quads BTU of electrical power last year, but only 12.9 quads got to the end user. We lost 65% in transmission. Okay, now most people think that electricity flows down the wire like water does a hose. No, that's not the way it goes. It's the excitation of electrons from one to the other. And as that distance goes, that excitation reduces, and so you lose power. So what's the holy grail? What's the holy grail of this? A superconducting alloy. So right now, our best superconducting alloy is a copper oxide, thorium, thallium. We have another one?
Must have been the Marine repaired. So our best superconductor right now, our highest temperature superconductor is a copper oxide, thallium, thorium, mercury, and barium alloy. And it becomes superconducting at 110 degrees Kelvin. If you're not a physicist, you know that that's pretty cold. That's equivalent to minus 220 degrees Fahrenheit. It might be really good for manufacturing on the far side of the moon, but not here. Not here. We still have a ways to go. So, where are we going to be using electricity? How much electricity is AI going to require? About 114 trillion watts. Okay, so if we can't send it long distances, I think what we're going to have to do is the AI people, they're going to have what we call microgrids. They're going to have to establish their own microgrid, maybe a small new power plant, in order to provide the electrical energy needed for AI. Because we certainly can't support it right now. So we look around and we say, what's this guy talking about? You know, microgrids and small nuclear power plants. Okay, isn't that stuff dangerous? Well, if we took all of the high-level nuclear waste, it wouldn't even fill this auditorium up to the first window. But it's really bad stuff. Okay, so looking at a microscope level, probably the next Nobel Prize in physics is going to be given to someone who's working on the transmutation of nuclear waste, turning it into isotopes that have a half-life not of 250,000 years or 5 million years, maybe into 50 years, so that we can actually handle it as a civilization. So we take a look at how electricity is used, only about 2% now in transportation, 13%, 25% going to industry, 39 going to residential, and 36 going to commercial. And of course, this leads us to leads and back retrofitting buildings and things like that to save energy. But even if we did, if we could save that by 50%, we'd still only be saving maybe 5 or 6 quads of electricity. This is a huge number. So the world energy consumption caused by friction is more than what the United States produced last year. I want to say again, world energy consumption caused by friction was more than the energy that the United States produced last year. 1.1 or 101.3 quads. So you know where this is going. I want to reduce friction, because this really could be low-hanging fruit. So what is this friction and wear? Who's the tropologist in here? Yeah, I brought my own tropologist so he could raise his hand. Who's in physics? Chemistry? Okay, little lesson. This is the first historically documented use of a lubricant. 4,000 years ago, some guy was pouring a liquid in front of that sled to help move that sled easily so that those people wouldn't be whipped so much to get the statue to wherever it's going to go across the desert. 4,000 years we've been dealing with friction and wear. at least documented. So what is this? It's nothing but a resistance force because no surface is smooth. Even molecules are not smooth, even at the molecular structure. So this friction occurs because we have rough surfaces and they're sliding over one another. Even under magnification, if I take a look at a very shiny ball bearing and I magnify it enough, I can see that that surface, although it reflects light, what shiny does is extremely rough. And this is, well, that's small enough where you can actually see the carbon and the carbon steel in the matrix there. 65% of equipment failure is attributed to wear. We're talking about people, profit, planet. If we can reduce wear, that seems to really improve their profitability. Things won't wear out as quickly. Things will last longer. So how does equipment fail? About 10% is obsolescence. So if you're the owner of a coal-fired power plant, your equipment is failed by obsolescence. Okay? As you have a dirty source of energy. Breakage. Who hasn't broken glass? To me, breakage, I immediately think of a forklift driver, right, Penny? In manufacturing plants, they break everything. They beep just before they break something. Okay, and then 80% of surface degradation, 15% of that surface degradation is called corrosion. That's why we paint. That's why we paint and use correct protective coatings. And 65% is wear related. 30% adhesive wear, 25% abrasive wear, 8% surface fatigue, 2% corrosive wear. All of these wear types, there's only 4, but we call them by a lot of different names. But this is what happens is adhesive wear, typically we just have 2 metal surfaces coming in contact at the asperities because we've used the wrong lubricant. Lubricants are not just slippery and wet. They have to be designed. So what we have is the lubricating film is insufficient either due to high loads, high temperatures, or high pressures. Metal surfaces come in contact, they cold weld, transfer material. We call it storing, galling, seizing, smearing, and scuffing. Okay, those are the typical terms that a layman would use to describe something. So, my first focus when I see this type of wear is I look at, is it the correct lubricant viscosity? Which is simple enough. The next one would be, does it have the correct fit-for-purpose additive package? I come from almost 20 years of developing and selling additives for a little company called Lubrizol, which is the world's largest. So that's what I would first look at. Very first law of lubrication, and what is that, Professor? Viscosity. How many times did I use the term viscosity in the three-day training courses I gave? About 100 times, just to beat it in to people. Okay. It's the most important physical property of a lubricant, especially if you want to prevent adhesive wear. You've got to keep the metal surfaces separated. Then we have abrasive wear. And oh, by the way, adhesive wear generates wear particles. We call that two-body wear. And then we have outside particles that cause three-body. And it's caused by hard particle contamination getting between the moving surfaces. We call it polishing, storing, scratching, grinding, gouging, and erosion. So if your lubricant is contaminated, well, this is not fit for purpose. It's going to cause more friction and wear. So my first focus is always lubricant cleanliness, preventing contamination, which is about 10 times less expensive than controlling contamination. So the second law of lubricants is cleanliness. So here, courtesy of Michelangelo, okay, is God giving man an oil filter. And the devil got involved in reversing filters to make them last longer. That we were talking about earlier today. Then we have fatigue wear. Fatigue wear is typically, it happens over many cycles. It's sort of like bending a coat hanger. You bend it enough times, it breaks. Or if you bend the coat hanger extremely large part, then it breaks because of the forces generated. So typically we find this in roller bearings, okay, where everyone realizes that metal surfaces are elastic, right? Okay. So what we have here is that every time that bearing rolls at the contact, the bearing becomes flat, and the race becomes slightly round, and then it springs back. So that's like bending the coat hanger many, many times, is the deflection of the bearing surfaces causes fatigue. So we call that pitting, scalding, Brunelling, indentation, cracking, flaking, and delamination. We have a lot of terms for fatigue wear. So my first focus is either it's an overloaded surface deformation or it's hertzian cyclic deformation. My first focus is always going to be on load. If you increase the load, the life of the bearing is decreased exponentially to less than 1/8 of the bearing life. Then focus on speed, and that's my Hertzian deflections, the number of Hertzian deflections per minute or whatever. So if you double the speed, the bearing life is cut in half. And then my third focus would be to look at the metallurgy itself. Is the metallurgy sufficient for the load and the speed that I'm trying to apply? And then finally, corrosion. It could be surface or intergranular below the surface, and its exposure to a reactive environment, whatever that may be. Okay. Typically, the reactive environment is water. Things rust. We get fretting lines caused by moisture getting in between the surfaces, causing that. Process fluids, what I mean process fluids, I mean things that we pump, things that we have in refineries and chemical plants, the reasons why we have mechanical seals to sort of seal the process fluid away from our bearings. And then my second focus would be on lubricant oxidation, because as we forget to change our oil, it undergoes a chemical process called oxidation or nitration, since the air we breathe is about 74% nitrogen, 23%, 21% oxygen. So focus on that because that makes your oil acidic enough to corrode on the surface. So all we have to do is control for easily identifiable and recognize types of wear. It's as simple as that. We've been trying to do it for 4,000 years. What's the true cost of lubrication in our country? Total U.S. automotive and industrial lubricants 2023 was valued at only $26.8 billion. And it's expected to grow to about 37.5 by 2033. So we spent almost $27 billion on industrial and automotive lubricants in this country last year. Now, we talked about the energy. Now let's talk dollars. Okay, how much money did friction wear cost us? According to the Energy Information Agency, the direct cost of friction wear accounts for about 8.31% of our gross national product. Last year we had a gross national product of about $28 trillion. So last year, friction wear cost us $2,336 billion. That's so good. I get goosebumps thinking about the money that we just throw away. About the money. We haven't got it right in 4,000 years. Right, Kenny? We still haven't got it right. Then we go to an organization that I belong to, the Society of Tribologists and Lubrication Engineers, and they said 10% of that friction and wear cost could be eliminated by just simply using the correct lubricant. And that's where my training comes in. This is what I focus on. This is my passion. This is my passion, is for people to use the correct lubricant for the application. And that is $233 billion potential savings just by doing something right. Which is 9 times more than what we actually pay for the lubricants. That's also an amazing number. So people, I think one of the great opportunities that Great Plains Center of Excellence has of doing energy audits is also maybe helping to conduct lubrication audits with proper training. And I'm here to help you. So that's our potential across the country. I'll take 13 states worth of that, won't you? Okay. You think that'll be a good return on investment for the Department? Who's the owner? Yeah, Department of Energy, right? Did you know all these numbers? No. You know why? Because they don't come with pictures. It's the most boring report I get on a monthly basis. And so I have to put them in picture format so that people can understand. Nobody knows what a quadrillion is. That's a big number, but how much, it's 15 zeros. It's 15 zeros. And you talk about a kilowatt hour. That's minuscule compared to that. So that's our potential savings. That's why I'm excited to be here. That's why I'm passionate. So how do we go about selecting and using the right lubricant? It would be nice if the first thing people did was read the owner's manual. Who has read the owner's manual for the vehicle that you drive? Raise your hand. Raise your hand high. Only mutants read manuals. Raise your hands. Okay, raise your hands again. Okay, see the mutants and okay, only mutants read manuals. I have gone into very respectable and revered manufacturing companies. You look at the technical library, and there's still cellophane on the manual. I guess they don't want to get dusty. I say the secrets of the universe are contained in manuals that no one reads. And then, you might read it, if you read the manual, they might tell you what they thought would be severe or regular normal service, what that is. And then after I read the manual, I would look at how I installed that piece of equipment, how I have modified it. Because what the United States is, who's the entrepreneur? All right. We've got entrepreneurs. We have tinkerers. We tinkle, okay? We will take a perfectly good Corvette Z1, what is it now, 600 horsepower? And we'll buy a ship that will give us 650 horsepower, right? We're gonna tinker with our toys and our equipment. I've had engineers send me parts, and they say, well, this is what happened when we installed a 150 horsepower motor on this mixer, and we replaced 100 horsepower because we thought we could mix it just faster. And of course, the gears all chewed out and everything because we tinkered and we broke. Okay. We didn't take into consideration 4 critical machine parameters, which I call load, environment, temperature, and speed, or less. I try to keep everything simple. I teach professors, and I teach lube technicians with a high school diploma, or maybe not even a high school diploma, this technology. And they go back and they make a difference. They can make a difference. So if we're talking about load, we've got static loads, dynamic loads, and shock loads. Okay? Now, if you happen to be purchasing electricity in a manufacturing plant, you're paying for peak load, because that's what the utility needs to build for. So after the peak loading, you get into your dynamic load or your steady state load. So yeah, that's just maintaining momentum. And then you have your shock loads causing severe stress. That's when you break things. Then we have environmental parameters that have to be considered. What are the normal working conditions that may be located in the manual that nobody reads? What are the abnormal conditions that may also be contained in the manual we do not read? And then we have to consider our own environment, the dirt, dust, and sand that's in the air. People scratch their head and think, well, how do those wind turbine blades wear out so much in West Texas? Has anyone been in a dust storm in West Texas? Guess what? There's a dust storm every day in West Texas because the air is dusty. And the tip of that wind turbine is doing 235 miles an hour in a dusty environment. And so we wonder why wind turbine blades wear out. Water and humidity, processed chemicals and solvents. Clean in place detergents, we do a lot of work with the food processing industry. And they're always cleaning their equipment. Gases, smog, even vacuums. Okay, only certain types of lubricants can work in outer space. Unfortunately, they're all PFAS. So we're gonna, by the time we colonize Mars, we'll send them on a rocket ship that's lubricated with fluorinated lubricants, and we'll all have mutants living on Mars. We haven't figured that one out either. Different temperatures. Ultra low temperature, anything less than 40 degrees for a hydrocarbon lubricant. Normal, low temperature, less than 40. Your normal operating temperature, more than 40, but less than 200. And and then high temperatures, and then extreme high temperatures. For a hydrocarbon, extreme high temperatures above 400 degrees Fahrenheit, those liquids don't last very long, they have to be lubricated. Then we have different speeds. Okay, and then for years we were only talking about ultra low speed, medium speed, high speed. Your medium speed are where your electric motors are. Your high speed is probably where your teenagers drive their cars or drive a motorcycle. Ultra high speed greater than 10, and then now I call it Tesla speed. Tesla speed has to be accounted for greater than 20,000 RPM because that's what the electric motor turns at, going through a 3-stage gearbox, right? So now we have what I call Tesla speed, greater than 20,000. Well, we have to take all of that into account. Why? Because low environment temperature and speed directly impacts how things are out. Bringing it all back into the circle, it's roundabout. We don't read the manual. We increase wear and friction. Because load, remember what I said? You double the load, varying life is reduced exponentially. Well, adhesive wear, load, speed, and temperature. If my oil isn't correct and it can't stand the operating temperature and thins out, guess what? Metal surfaces come in contact with them. If my speed is too high and my viscosity is too high, then the oil can't get into the high-speed contact. Okay. If my load is too great and my oil is too thin, it gets squeezed out quickly. My environment, all the dirt in our extremely dirty environment. If you read the newspaper, who reads the newspaper in the morning anymore? You know, we get everything online, but in the old days, when I read the newspaper and I had a sunbeam coming through the library, and I'd sit back and I'd see all those little floaters. Those are dust particles, the ones that you can see. It's like they say, it's what you don't see that can hurt you. And then, of course, load and speed, because load and speed is going to produce my adhesive wear particles that will also result in abrasive wear. And then my surface fatigue, load and speed, and my corrosive wear is going to be environment and temperature. That could be, yeah, well, that could also be in your corrosive wear. Yeah. So the relative size, this is always, cigarette smoke is 1 micron. Okay. Lots of refineries literally lubricate their bearings with a mist of oil. With a mist of oil. During COVID, you know, I was out in the backyard smoking a great Cuban cigar, and my wife and her friends were playing outside with masks on, canasta. And one of the neighbors said, "Oh, John, zero lot line," so the smoke had to go all the way over her house into her side. She said, "Oh, that cigar smells great. Is it Cuban?" I said, "Yes, it's a Cuban. And if it were a virus, you would all be dead now." Because you can smell it through your mask and it's only 1 micron. And the COVID virus is 80 nanometers. So, and why do I focus on the small stuff? Because we lubricate with extremely thin films. A journal or a slip bearing about 5 to 10 microns. We get down to rolling element bearings, 1/10 to 1/2 of a micron. We're looking at nanoscale thicknesses of lubricating fluids. So guess what? We got to get it right. Okay, and what's happened over 4,000 years? What's happened with our machinery Maybe she's a mechanical engineer. Oh, there she is. And what did I say? Oh, you're going to make things and you don't even know how to lubricate them because you've never had the training. Okay. When I worked for Lubrizol, every time the automotive industry came out with a new motor, they designed it, and then they came to the oil industry and said, hey, you guys have to improve your lubricant to protect my turbocharger, or to protect whatever, because the tolerances and the temperatures were all changed. And so yes, so in 1980, it was SF for passenger cars, and then ST, SH, SI, we're now SP, right? That many changes in 40 years because the engine technology changed, the oil technology never changed with it. The only thing is the oil technology only changed after the problem showed up. After the problem showed up, that we changed the oil technology. So, why do we do this? Well, on the practical side, which we've been doing for 4,000 years, reduce friction, minimize wear, reduce heat, seal out contaminants, prevent rust and corrosion, transmit power hydraulically. But the sustainable reasons, which is why we're here, the sustainable reasons is improve machine reliability. Because if we don't improve machine reliability, that center work profit between people and planet doesn't happen. Next is reduce energy. So if we finally get it right after 4,000 years, and we reduce friction, and we reduce wear, we can also reduce our energy use at the tune of $233 billion in this country. Extend machine life, save on capital, reduce maintenance repairs, reduce operating costs, and finally, to reduce our carbon footprint. So what's the true cost of lubrication? Well, right there at the top, equipment reliability, energy or fuel consumption, the cost of facility downtime. Just read an article a few months ago from Manufacturing Magazine, is that 1 hour of downtime causes the typical medium-sized manufacturer to have $150,000 in cost per hour. And that's across the board. It doesn't matter if you're doing medical supplies, parts manufacturing for the automotive industry, my plant, okay? $150,000 per hour. It's employee health. Okay, I'm very passionate about this. Took us 21 years to reinstall the reportable Tier 1 carcinogen emissions from our plant. 21 years it took. Okay, but that was a passion. I lost a wife and 2 sons to cancer. It's home. Now you can do things right, or you can do the right thing. And when you do the right thing, you become a leader. If you do things right, you're a technician. So it's employee health. It's the cost of equipment, precision, and scrap. Well, guess what? If your machines are wearing out, they're not making widgets to precision anymore. So now you've got more scrap. It's the service life of the equipment at capital costs. It's the cost of environmental compliance. And oh, by the way, it's the cost of lubricant misapplication by not reading the manual, by not considering less. It's the cost of over-lubrication, it's the cost of under-lubrication. And that's where this organization, for training, can have a direct impact when we go out to energy audits, make recommendations for small businesses. It's a big pile of money. So, some interesting technologies that we're looking at just like a Google car driving in your neighborhood, taking a picture of the neighborhood. We'll also talk about some bio-based synthetic base oils that are coming into the market. So this is the MapVest 3D mapping for digital plumbing of a facility. This is to the scale now where one person can walk through a plant in about 30 minutes to an hour and get a digital map of the whole thing. Now, why is this important? Well, it's pretty important for one of our companies. We have, what, 51 plants? We're going to digital map all 51 plants. We're going to have a digital clone. Because 2 years ago, I was at Eli Lilly in Indianapolis, and they showed their digital clone of a facility in India making pharmaceuticals. And there was a machine went down, and I was able to go into a room with the experts, put on my virtual reality glasses, and I could see the machine in India. The exact same machine in India, we had a digital clone that I was looking at. And so the technician could be walked through by the experts on fixing this machine, repairing this machine in the least amount of time. Because I'm sure that that Eli Lilly facility was losing more than $150,000 an hour. So it's 4 cameras. We're also looking at maybe even being able to use infrared as part of this, and looking at hotspots for motors and things like that to give somebody a really quick readout on the efficiency of their electrical system. You know, we could use this technology. I can take every one of your temperatures and see if you have a fever. What's this? So this is an exterior cloud point. He was not in the hot air balloon. This is what's so neat. He was not in a hot air balloon to do this photograph. He walked through the plant, but he got the coordinates from Google Maps. And so we can look through here. This is a Google map of my facility in Tulsa. It's almost like looking down through a glass and looking at my facility. And we can use this point cloud for snippets to export into CAD/CAM so that people can have drawings of their facility, as opposed to a schematic, which everyone has a different schematic that you're trying to look at for their process. So this is actually looking through the roof of my facility. And so that's one of our reactors. And then this is the point cloud picture in here, and you can remove people standing in the way. Okay. You can eliminate them out of the picture, and then you can take that point cloud, turn it into a high-resolution panoramic photo, which is suitable for virtual reality. And I'll be able to put on my virtual reality glasses and give Chris or manufacturing guy help. Yeah, well, I think you should do it this way. You know, we'll put the non-experts behind the glasses. that could be a liability for that. But now you can do points of interest, motors, pumps, bearings, even lubrication points can be documented, and that can all go into a computerized maintenance management system. So this is the hardware. I really wanted to show you, some of this. You need a really good computer. It's not your normal laptop that you can manipulate this data. So this is what you need to manipulate the data. But it does support two computer maintenance management systems right now. Any questions on that? It's a really neat technology. You've got a grad student who's getting involved in this. needs to talk to Kenny and a couple of people. Now I want to talk to you about biosynthetic lubricants. Biosynthetic oils can be drop-in substitutes for petroleum-based oils. They just have a different molecular structure. Okay? And bio-based is circular by definition. I love this. Plants and microorganisms take in CO2, use the sunlight, build biomass, either lignin, xylem, wood, sugars, or vegetable oils. And so it's a circular process, something that we've been looking for a long time. The Stone Age did not end because we ran out of stone. Okay? That was 4.5 million years. That's how long the Stone Age lasted. You'd run out of stones after 4.5 million years. Okay, and I think the Bronze Age was like 2,000 years old. The Iron Age was like 800 years old. The Steam Age was only less than 250 years old. And now the Petroleum Age started in 1907. So how long did that last? We don't know. But we do know that can be used for lubricants and greases. Now, if you take a look at a typical lubricant, a hydrocarbon lubricant, the biggest polluter is the base oil, typically 65 to 100%. And in the United States, that was 30 billion tons of base oil used in lubricants. Then we have about 8 million tons of additives, which are specialized chemicals that may or may not be harmful to the environment. We try to use ones that aren't. So this comes from the American Petroleum Institute. You know, they should all be in prison, right? No, they shouldn't. Okay, but they group their base oils, or the base oils used for lubricants. The first one is mineral oil, with more than 300 parts per million sulfur, very low viscosity index, and we manufactured almost 3 million tons in America. The next one is a Group 2 mineral oil, and once again, we manufactured almost 4.5 million tons, or 96% of the base oil we produce in the United States was that stuff. You can see over in Asia, they're not producing as much Group 1 nasty mineral oil because they've got newer refineries. We haven't built a refinery in the United States since 1974, and that one was a small one. Then we have Group 4, Group 3s. This is a Fischer-Tropsch method. This is typically, right now, being used to take stranded natural gas and turn it into a liquid fuel and liquid lubricating oils. Shell is probably the premier manufacturer of this technology. But it only accounts for about 4% of the market. This is what we use. This is typically our lowest quality base stock that we use. It's only about 304,000 metric tons. Then we have PAOs, polyalpha olefins. This is 50-year-old technology. This is the basis of Mobil 1. This is their technology. And worldwide capacity is only 780,000 tons. So there's not a whole lot of synthetic lubricants out there on the world scale, even in the United States. And then we have bio-based, and that is a biosynthetic that we manipulate in what's vegetable oil that we eat, cook with, spread on our toast in the morning, called margarine. Okay. And the world capacity is only about 400,000 metric tons of vegetables. So if we take a look at mineral oils, they literally come from the bottom of the barrel. Okay? The lubricating oils come from the bottom of the barrel. Okay, that's the source. And oh, by the way, they come with 2 carcinogens. These carcinogens literally mimic the structure of your DNA. So if you inhale them, eat them, or absorb them, they do bad things to your DNA and cause cancer. These oils cannot be used in newer cars, which require a 0W or a 5W multi-weight motor oil. So all of these nasty mineral oils are going into the industrial sector. Fischer-Tropsch, really neat technology. It's about 80 years old. It can turn coal, natural gas, or biomass into synthetic plastics, rubber, synthetic gasoline, diesel, and also a base oil, a branched paraffin base oil designed for lubricants. This is the Mobile One technology. It takes ethylene gas at the top of that distillation tower, turns it into a uniform synthetic hydrocarbon. This is a trimer of that product, molecular trimer of that product. Now, we can take regular vegetable oil, which is not a very good lubricant. Okay. I mean, how long does McDonald's keep their oil to fry French fries? Like, they get rid of it every 6 hours? Who's worked at McDonald's? No one? Okay. But now, we can take a vegetable oil, put it through a manufacturing process, and we can turn it into a synthetic vegetable oil molecule that looks just like a synthetic petroleum molecule, which has a lower coefficient of friction. Duh, we've only been working on this for 4,000 years. Maybe we're going to get it right. And looking at group 3, group 4, and this new bio, we can actually see we have better low temperature properties and better weather properties. So we're going to use it, I hope, everywhere. But at least we can start here. Any environmental sensitive area or accidental loss. The biggest people who are interested in this are trash haulers. Because when they have a hydraulic leak, it's always in your neighborhood. Actually, Kenny had a trash hauler accident in his lot last year that had to be cleaned up. And there's no compromise. Any questions? There's a whole lot going on. We are living in a great opportunity right now. Like I said, we're already done with Generation Z. So now we get to go back to Generation Alpha, and maybe we'll get it right. Maybe we'll get it right. So there's a whole lot of opportunity out there. Entrepreneurs, they're welcome. You're the backbone of the tinkering culture that we have in this country. Any questions? Yes.
You said the distribution, you're looking at the savings that manufacturing happens because some are really doing that. Most are okay, or is it like just across the board?
It's pretty much across the board that everyone. We've only been doing plant for 25 years. Plant surveys where we go in, we save some tons of money. Going through, actually getting the engineers to open up the technical library, going through, documenting how they changed it. A gearbox works differently if it's horizontal or it's at an incline. And how much lubricant to use and things like that. People just don't take that into consideration. Yeah, so we see we saved Blue Stripe, how many $millions per year? We reduced their electricity consumption at their plant by 13.5%. All right, thank you so much for listening to me spout off about the opportunities that we have. And I think and the neat thing is